Hello, we are Team 19085, presenting our project, the Virtual Reality System for Treating Eating Disorders. This project was sponsored by Dr. Marvin Slepian and the Arizona Center for Biomedical Innovation. My name is Nancy Pham. I am the team lead studying biomedical engineering.
Hi, my name is Alex Reyes, and I'm an electrical and computer engineer for Team 19085.
Zaina Kmed, studying biomedical engineering.
Hi there, my name is Steven, and I am the systems engineer for Team 19085.
Hi, my name is Carm, and I'm a biomedical engineer.
I'm Kurt Bansel, and I'm an electrical and computer engineering major.
Here is a copy of our poster covering the information we will elaborate on throughout this presentation. Please feel free to pause the slide if you'd like to take a closer look. Eating disorders have a significant impact on individuals' lives, the healthcare system, and the economy. With approximately 30 million individuals suffering from it in the U.S., it has the highest mortality rate of any mental illness. Our group is trying to make a dent in the health impact of these disorders using virtual reality therapeutics. Benefits of this therapy are summarized below, and Zaina will walk us through how it ties into our project.
The objective of our project is to offer a treatment for certain eating disorders via a virtual reality simulation. To do this, we have designed a multi-level, multi-branching virtual reality simulation to expose patients to a variety of eating situations. During the simulation, physiological data will be recorded and the patient will be asked to fill out a self-evaluation at the end of each level. This is important for helping the physician better understand the correlation between stress and the simulation progression for each individual patient. Taking this information into consideration will be key in the development of an individualized treatment plan to desensitize patients with eating disorders to stressful situations involving food.
This is our system block diagram. It shows the main components of our system, which is our sensors, our CPU, our Oculus Go virtual reality device, and our virtual reality simulation, and how they all connect together. So one of the largest changes that affected our project was that our sponsor, Dr. Slepian, changed our project to remove the blood pressure sensor and instead implement a galvanic skin response sensor.
Here we have the simulation running. You can see the user is in an environment where they can look at the 360-degree video that we recorded. The user right here is walking to the fridge where they're going to make the first food selection for the scenario. They're going to be given the option between the soup and the spaghetti there, and the user can pan over to the spaghetti with the remote, select spaghetti, get shown the video of being selected the spaghetti, and it'll load the spaghetti portion size screen where they can choose 3 different sizes of spaghetti, small, medium, or large.
For our narrative, we have 3 different eating scenarios. The user will experience eating alone, eating out, and at a potluck. In each scenario, the user will go through a series of decisions that will determine if they'll move on to the next level or repeat the one they are in. To level up, the user must choose a combination of foods that are within plus or minus 15% of the target calorie amount, which is half of the daily intake that the user must consume in order to maintain their weight. This is determined by the age, weight, height, and sex of the user, as shown in the equation below. Because our system has predefined foods with specific calorie ranges, users with higher or lower BMI would not be able to use the simulation successfully. For this reason, the system will multiply the calorie ranges by a ratio of the user's BMI over 15.6 to ensure that everyone is able to pass each of the scenarios.
We chose this component after extensively researching various heart rate and galvanic skin response sensors. The E4 wristband met the criteria for a system, including the ability to read normal ranges of physiological response, comfort, ease, sampling rate as defined by the ability of the sympathetic nervous system to exert detectable and measurable effects on the body, and the capacity to collect and display data in real time.
This flowchart on the left outlines how the connections made between devices are used to produce a real-time graph of data received from the E4 wristband. Starting from the top, in order for the E4 streaming server to be able to make a connection to the E4 wristband, a dongle needs to be connected to the PC that's running the server. Once that connection has been made, then the wristband can send channel data to the server. Next, the connection between the TCP client and the streaming server involves the TCP client sending commands to the streaming server. These commands are used by the client to form its own connection to the wristband, as well as subscribe to channels of streamed data from the wristband. In this relationship, the server sends data from the channels the client is subscribed to in the form of data packets. The TCP client parses the packets and then plots the data to the graphing GUI in real time. This is the start point for the TCP client. When the user opens the client, it will wait for the user to press enter before making the connection to the streaming server. Once the user presses enter, then the client will automatically make the connection to the server, as well as connect to the E4 wristband and subscribe to the GSR and VVP channels as so. Then the graphing display will pop up, and when the user presses start, the data received from the server will start to be graphed in real time. Then, when data collection is over, and the user would like to terminate the application, they can press stop and the graph should stop plotting the data. Then they can close the graph and the console will cut the connection between the TCP client and server, which is shown by the device disconnect OK line below. The console will then wait for the user to press enter again in order to close the application.
For our project, we had to run 5 tests: accuracy and sampling rate of the heart rate sensor and the sampling rate of the galvanic skin response sensor tested even better than we had anticipated. The Oculus Go frame rate averages at 60 frames per second for our simulation, as we expected. The calorie counting and level up test ensures that the patient can only level up if they fall within our given calorie count threshold. And finally, the wireless communication test ensures wireless communication between our subassemblies. We were able to complete all of these tests on the subassembly level, and they all passed. However, due to the challenges with integrating our system, we have not been able to run a complete acceptance test on the integrated system.
In our project, we follow the engineering V model up until the system verification and validation. That was the last thing we did, and we have not put it into operation or considered lifetime maintenance. So during these 2 semesters, Team 19085 has created a virtual reality simulation with the hopes of using it to treat patients with eating disorders. We hope that Dr. Slepian will use this project to either help people or to use it as a base to build upon for next year's senior design project.
Here is our list of references. We would like to thank Dr. Slepian and the Arizona Center for Biomedical Innovation for sponsoring this project. We would also like to thank Daniel Palomares for his support in providing access to the lab and assistance in completing our acceptance tests. Finally, we would like to thank our wonderful mentor, Heather, for her unwavering support, guidance, and encouragement. We could not have done this without her.